we need to create antimatter and destroy the world. We wouldn't really destroy the world. We can't create that much of it. Anyways, let's come up with a solution to how much energy is needed for pair production to create an electron and its counterpart, a positron. So, how much energy would a photon need to undergo pair production for this electron and a positron? Well, to do this, we're just using Einstein's idea of E equals mc squared. And yes, I realize that that equation is actually a little bit longer when we include the momentum of light, because we are converting this photon energy directly into mass. We can ignore the quantity pc squared. So we can just start with E equals mc squared, an equation you've known about for years and are finally starting to use. Now, we are creating out of this energy some mass. The mass that we are creating is an electron and a positron. Now, a positron is identical to an electron in every way except it is positively charged, which means it has the same exact mass. So the energy we need is equal, because we've got an electron and a positron, 2 times the mass of an electron multiplied by the speed of light squared. That's how much energy we need to make both of them. And if we plug in values, we're going to get 2 times the mass of the electron, which is 9.11 times 10 to the negative 31st kilos, very, very small, multiplied by the speed of light, which will approximate as 3 times 10 to the 8th meters per second, squared. When we do this and we multiply all this together, make sure you square your speed of light. When you square that, that should give you 9 times 10 to the 16th. And then you multiply it by the 9.11 times 10 to the minus 31, multiply by 2. You should get 1.64 times 10 to the minus 13 joules. Which, if you wanted to put this into mega electron volts, or just EVs, you know that 1 EV is 1.6 times 10 to the minus 19 joules of energy, which means that this here will give us 1.02 mega electron volts. That's a lot of energy. That's a lot of energy. Now, if we know that we need at least 1.02 MeVs to create this pair production, or to cause this pair production, then the next question be, what wavelength of light would that photon be? So what is this wavelength of the photon? Well, we know that for a photon, the energy of it is equal to h nu, or Planck's constant multiplied by the frequency. We can also say, and we know, that this is equal to hc over lambda. And this lambda is actually what we're looking for, because we're looking for a wavelength. What this allows us to do is we can say that lambda equals hc over the energy. And if we do this, we know that hc is actually 1240 EVs nanometer. If we divide that by our energy, that was 1.02 mega electron volts, or 1.02 times 10 to the 6th EVs. Which, when we do this, and then we're going to convert out from the nanometers, we get a final answer of about 1.2 times 10 to the minus 12th meters. Note, I converted out of nanometers to meters at the end of that. And this corresponds to one of my favorite bands, Gamma Ray. We need gamma rays in order to have pair production. Another interesting kind of spin on that is that if we have an electron and a positron annihilate on their interaction, they'll give off light. The type of light they will give off will be gamma rays. And in our PET scans, our positron emission topography scans that we use in the medical field, the camera that they kind of put around you is looking for gamma rays. They have you ingest or inject into your body some substance. I'm not a medical professional. I don't know what that magic substance is. But it interacts with your body, and it forces electrons and positrons to interact, and we see out of that gamma rays. So it's a kind of wild thing that we see there, but it's useful in order to detect cancers, to see if cancer treatments are working well, to see if cancer is spreading. This kind of stuff saves people's lives. So this is our first foray into E equals mc squared, and it is our first foray into thinking about not only matter, but antimatter. And we can see how much energy we need and how much energy that kind of annihilation would give off. Until next time, though, this is finished. Adios, and take it easy.